crew from the UMaine did some geo-radar explorations of the mound and identified some kind of architecture under the sand cover, the thick layers of sand that cover the mound now. So my mission there was basically one of the field objective was figure out what was under all the sand. And but I also included some excavation in the other side. This is Los Morteros, and these are neighboring sites that were part of my research. And I also did some work to understand the physical transformation of the environment. Because the environment should have been very different than it is now to can host all this amount of archaeological sites. So this is an aerial photo of the mound of Morteros. It's a large mound. And to give you a better idea about the dimensions of the site, is larger than twice the area of this building. And but I'm going just to talk about what I found in those Morteros. I'm not talking about the other part of my research. So I'm going to start talking about the findings here from the earliest phases of occupation of the mound. These are the oldest evidence here, and going to the youngest, the latest phases. So the first phase of occupation, human occupation of the site, was found in this part, in the central sector of the mound, which is also the lowest part of the mound. Here, this phase of occupation, the first phase, consisted in a stone hearth containing ash, charcoal, fish bones, and scallop shells. The date, those dates on top are moved now. But the dates are very old, 57 to 54 calibrated years, 100 calibrated years BP. And I haven't excavated any other evidence related to this occupation, so I don't know if there was a kind of architecture or some other context associated with this stone hearth. But these were excavated in the deepest part of the mound, in the deepest deposit also that have been excavated so far in this site. So the second phase of occupation was found in the northwest side of the mound, and here I uncovered a large room, adobe room. It's a mud brick room with very high walls. In some places the preserved height was more than 2 meters. And it's a very carefully made space made of adobe, mud bricks, and with thick clay floors and internal architectural features. And it's a very complex type of architecture. This is an aerial photo of the same room. It's 10 meters long from north to west, and 7 meters wide from from north to south here and east to west. But something that is important here about the very important point about this architecture is that this is so far the oldest examples of adobes in the Andes, and these adobes are now under study to understand how these adobes were made and what is the composition. But adobes, the architecture that use these adobes, these mud bricks, are an ancient tradition in the Andes that lasted from the late pre-ceramic period to the arrival of the Spanish, and Los Morteros seem to be at the very beginning of this ancient tradition. The third phase of occupation was better preserved on the top of the mound. This is the top of the mound here. And there are some evidence of the same kind of occupation in other places of the mound, like here and here, on top of the mud brick structure. And these are this was a large room of again a large structure. It's a stone architecture. The calibrated dates are these, and these are younger than the dates obtained from the stone hearth, like saying that this was actually a later occupation in the site. It's almost a superficial occupation. And this room has round corners and stone platforms, stone surfaces, stone hearts, clay floors, and one particular thing is the presence of this standing stone. This architectural feature is a very characteristic thing from the late pre-ceramic sites on the coast of Peru, and this kind of standing stone that is called locally Huanca, which is a Quechua word. The Quechua is the ancient language of the Andes. So is the interpretation of the use of this standing stone is to calculate time using sunlight. So again here in Los Morteros, based on the radiocarbon date, this is the oldest example recorded in the whole Andean area, and which is a very interesting because this means that Los Morteros could have been the place where this kind of tradition originated and spread from. So this is an aerial view of the same room, an aerial photo, and you see this is a large room. I didn't find the other end of the room, but it was more or less should be over here. The preserved length of this space is 15 meters. And as you see, there are other rocks around, and this may be an indicator that there was more architecture on top. And something very important about this research is that this study has demonstrated that Los Morteros wasn't a natural mound, but an artificial one. And here are the dune fields, the map of the dune fields in the area. And you can see the Morteros are here in this red square. So this is not the area of sand accumulation. So the sand cover of the site is because there is something artificial, which is architecture that trap all the sand intentionally. So we have obtained a rate of sand accumulation using midpoints of calibrated dates from the deepest and oldest deposit and the latest and more superficial deposit. And from this level of the stone heart to the base of the mound, there are like between 10 and 12 meters. And if you use that rate of accumulation, this means that the beginning of Los Morteros goes back at least to 7,000 years BP, which is very old. And there are other places in Peru, but this means that Los Morteros has a very long history of human occupation. But more importantly is that Los Morteros contains the evidence of early monumentality, which early monumentality is the sign of a kind of social organization that was the foundation of civilization in the Andes. And if you remember maybe from any history class, the Andes was one of the origin of civilization in the world. So that makes Los Morteros a very special site. And I also did some work about to try to understand physical transformation at the site, like for example, stratigraphic exploration of the embayment using through test pits. These are all these pits are pits, but this is I'm going to save this for another talk. I want to thank my advisor, Dan Sandwise, all the members of my committee, and especially today the support that I got from the Churchill Exploration Fund that helped me in this research through all the stages of this research in the very beginning. And also I thank all these people and institutions listed here. Thank you very much.
Question? Okay. No.
The location is one of the few places I've had the opportunity of going with the Climate Change Institute. Location, obviously, is in a very desiccated area right now and quite a long way from many of the streams running out of the Andes. At the time, the 5,000 BP, that's roughly when the sea began to recede from that point. Is that correct? Was there any other source of water? I mean, fresh water in that area at that time?
Yeah, what I found is that there are the source of water by then could have been the groundwater, the water table that was is higher in the area, and there is presence of wetlands and remains of wetland and ancient wetlands in the area. And that could be a source of water there. And I'm still working on the interpretation of the stratigraphy to see, identify other processes of environmental transformation. Thank you.
Next up, we have Benjamin Burpee, who will be talking about bacterial nutrient limitation in Arctic lakes of Southwest Greenland.
Does this work? Great. All right, yeah, hi, my name is Ben Burpee. I'm a second-year master's student in the Department of Ecology and Environmental Sciences. This is my clicker. Today I'm going to be talking about bacterial nutrient limitation in lakes of southwest Greenland. I just want to start off my presentation by making the general claim that lake ecosystems are very sensitive to climate change, and that's precisely why you've seen so many presentations during the symposium about lake ecosystems. This is particularly true for Arctic lake ecosystems, and there's a couple of different reasons why this is the case. The first reason is that we all know in this room that climate warming trends are accelerated in the Arctic in comparison to other general global warming trends. This is a map of Greenland using the climate reanalyzer that shows this warming occurring. We work on the west coast of Greenland, right here in Kangerlussuaq. The melting degrees, the average of annual melting degrees has increased in this region the past 20 years by about 200 degrees Celsius, which is a huge change. This is especially significant for our lake ecosystems because they're underlain by a continuous sheet of permafrost, and permafrost is super sensitive to even minute changes in temperature. This can have potential impacts for our lake ecosystems. It probably has already, and it probably will continue to have impacts into the future. Specifically, permafrost contains a lot of nutrients, carbon, nitrogen, phosphorus, that it can transport into our lake ecosystems. This is important because Arctic lake ecosystems tend to be, typically speaking, chemically dilute. So they have very low solute concentrations, and this includes nutrient concentrations as well. Because of these low nutrient concentrations, they tend to be biologically unproductive. Because this makes sense, right? In order to grow and reproduce, you need sufficient quantities of nutrients. So potential impacts of nutrient subsidization from thawing permafrost, for example, could lead to changes in ecosystem function, increases in microbial growth, algae growth, stuff like this. So we like to say that our lakes are nutrient limited, therefore. And when we speak of nutrients in lakes, again, carbon, nitrogen, phosphorus, when we speak of nutrient limitation, there's typically always sufficient quantities of carbon. So we're really talking about the scarcity of nitrogen and or phosphorus in our lakes. All right, so in order to make future predictions about how this warming trend in southwest Greenland may impact our lakes in regards to their nutrient limitation dynamics, it's important to understand their contemporary status. What kinds of nutrient dynamics are occurring in these lakes today? So this is where my research question comes from. What are the seasonal and spatial patterns of biological nutrient limitation across lakes of southwest Greenland? To approach this problem, we sampled a suite of 24 lakes surrounding the town of Kangerlussuaq, indicated here. The 24 lakes are these pink dots here. These lakes were sampled for the sake of the study, the data that I'm going to show you today, in 2013. We also went back in 2014, and we're also going back this summer. I'm going to show you a specific example. Although I make like broad characterizations across all these lakes, I'm going to be showing you a specific example of two lakes from the Nunatak here, SS32 and SS86. So I just wanted to provide that for your reference. So in order to infer kind of the biological nutrient limitation patterns that are occurring in these lakes, we used bacterial enzyme activity assays. So what are bacterial enzyme activities? How do they work? Who cares? Well, I have a cartoon here that kind of just shows some general bacteria maybe floating around in any given lake. These bacteria are super happy as long as they have sources of nitrogen and sources of phosphorus available to them. However, let's say in this scenario that their resource of phosphorus dries up for whatever reason. What these bacteria are going to do are they're going to secrete enzymes out into the environment. These enzymes are going to target large complex organic molecules that typically in their current state are just useless to these bacteria. However, these enzymes are going to cleave these phosphate groups off of these organic molecules. These small simplified phosphate molecules are then going to be released out into the environment and are going to be biologically available for uptake by these bacteria. What's really nice about these enzymes is that they are nutrient specific, and they're also secreted in response to nutrient scarcity. So by looking at the enzyme activities in the water, we can determine what the bacterial demand for things like carbon, nitrogen, and phosphorus are. And that's precisely what I did. And so this is kind of a trend that I found early on. I presented it last year Here it is again. It's an interesting trend, a tight correlation between bacterial demand for phosphorus and dissolved organic material concentration. This is a log scale on the x-axis. It's an interesting trend. Reasons why this might be happening, I'm not really sure. Perhaps there's some very bioavailable labile forms of nitrogen associated with the pool of dissolved organic matter in our lakes. And so therefore, this is putting bacteria into phosphorus limitation. Perhaps that dissolved organic material has more complex organic forms of phosphorus associated with it. And so bacteria have to work a little bit harder in order to digest these organic compounds and to acquire that phosphorus. But regardless, this trend doesn't really tell us much about bacterial nutrient limitation patterns in our lakes. In order to get closer to answering my original research question, the next approach I took was just to compare bulk enzyme activities across seasons in our study lakes. And the bulk enzyme activities, of course, indicate carbon demand, phosphorus demand, and nitrogen demand. And what I found was there was significant increases from June to July in nutrient demand by bacteria. And this is regardless of whether we look at the shore, the top, or the bottom of the water column in the lake. Now, there's a problem inherent to this approach, however, and that is I could indeed be looking at an increase in nutrient scarcity from June into July. However, it could also be a reflection of increased microbial biomass from June into July. This intuitively makes sense. The more microbes you have, the more enzymes that they're going to produce just by virtue of their sheer numbers. To get around this problem, we can kind of standardize the demand for phosphorus and nitrogen by looking at the interaction between enzymes. And when I actually did this, this trend was no longer significant. So there was no longer a significant increase between seasons. This is not to say, however, that nutrient limitation dynamics remains static between seasons. In fact, it's quite the opposite. We just have to look at the interaction between enzymes in a little bit more detail. And that's precisely what this graph does. It's a complex graph to take in, so I don't really want to get into the specifics. But what I want to show you is that there's two lakes here for an example, SS86 and SS32 from the Nunatak. These lakes, the time points are from June into July. What we can say about this graph is that it's divided by this line. This line has a slope of 1. On this side of the line, we get an area that indicates phosphorus limitation. On this side of the line, we get an area that indicates nitrogen limitation. So we can begin to see a pattern here. SS32, for example, is phosphorus limited in June, early on in the spring. However, by the time we get to July, it's nitrogen limited. We can quantify this limitation by measuring the magnitude of the angles of the data points from the origin. Furthermore, we can measure the magnitude of this vector, so the length of the arrow, in order to calculate bacterial carbon acquisition. And so we can see that bacterial carbon acquisition becomes greater in SS32 come July. In comparison, SS86, which is right beside SS32, has no change in nutrient limitation pattern between the seasons. And it also has a decrease in bacterial carbon acquisition from June to July. So kind of like an opposite trend almost. I'm just showing this up here for an example. I used this approach to analyze all 24 lakes, and a really interesting story emerged when the data was analyzed in this way, and that is a significant increase across lakes from phosphorus limitation early in the spring to nitrogen limitation later in the summer come July. And this is a general trend across all sample lakes. So in conclusion, I just want to say that inferred nutrient dynamics in our Southwest Greenland Arctic lakes are complex, in case you didn't pick up on that. There's increased phosphorus demand in response to an increase in dissolved organic matter concentration within our lakes. Lakes can differ in their nutrient limitation patterns, even lakes that are right beside each other, as we saw in the previous example. Generally speaking, however, there's a significant movement from nitrogen limitation early in the spring towards, P limitation early in the spring towards nitrogen limitation come July. So this study will be important to determine how nutrient dynamics may change in response to regional warming in this area. And finally, it was just nice to use this approach that's very common, bacterial enzyme activities, to use this approach to study these kind of pristine dilute Arctic lakes that are really kind of unusual aquatic ecosystems. So with that, I would just like to acknowledge my advisor, Desmond Saros, my lab mates, funding from the Dan and Betty Churchill Exploration Fund in particular for making this possible. I really appreciate it. Thank you all. Yeah.
Are there any birds that frequent or visit these?
A lot of Canada geese, yeah. So there's a lot of bird droppings, of course, on some of these lakes. Yeah, absolutely. We haven't really looked at that as a consideration, although I think we may in the future. I think we have a student coming into our lab maybe that might be interested in bird droppings. Yeah.
I was wondering how you know that bacteria secrete more enzymes when the nutrient.
It's an interesting question.
It's like in the environment. They say, I guess maybe in a laboratory setting, but then also in your environment.
Also in the environment. So how we have proof of that? Proof that bacteria secrete more enzymes when they're nutrient limited?
I guess so. Maybe not even proof, but why you
Yeah.
make that assumption.
It's a great question. I know that in this study, this notion is supported by chemical nutrient data, which is really nice. So measuring concentrations of inorganic nitrogen sources, comparing that to the sources of phosphorus, the ratios of our bacterial enzyme activity match up pretty well with those concentrations, which suggests that the bacteria are responding to chemical nutrient concentrations. So the chemical data, in other words, is supporting the biological data.
But you don't necessarily have a population of bacteria. Can you measure the population, like can you say how many?
Absolutely, yeah, and I haven't done that, but you can definitely look at like bacterial abundance and things like this, bacterial biomass you can measure. The notion of kind of normalizing or standardizing the enzyme activities to carbon acquisition kind of is a way of it's a proxy of bacterial biomass. So we can kind of account for that. Yeah. Yeah. Hey, Ben.
You thought about naming the lakes beyond the letter and number acronyms?
It's like, I don't think it's possible. I think they're all like SS. So there's a couple of different naming scenarios, I believe. And I'm trying to remember what they are.
Not allowed to by law.
Not allowed to by law? Okay. So there you go. It's against the law to name these lakes. Don't even try.
All right, next up we have, we're gonna move on, yeah. Nelson and Groff will be talking about climate change in the Falkland Islands, a new paleoclimate proxy.
All right, thank you for the introduction. So today I'm going to talk about a new proxy that I'm developing to reconstruct past climate change in the Falkland Islands. And the Falklands are at the southern tip of South America. And this is part of a broader question that I'm asking in this system that's looking at how abrupt climate change influences what I'm calling a marine terrestrial link. And you can see this link in this picture. So we have penguins here, and in your imagination, you might not always think that penguins and grasses go together, but here in the Falklands, they do. And there's a really tight mutualistic relationship between the penguins and these tussock grasses. So the penguins or seabirds and marine mammals are bringing in nutrients in the form of guano from the marine environment and depositing it, and these plants need this in such a low productivity environment. And in turn, the plants provide critical breeding habitat for the seabirds. So these tussock grasses are really important for sustaining the biodiversity in the Falklands. as well. And sustaining the biodiversity then promotes tourism, which is a natural strength in the Falkland Islands and a really big component of their local economy. And they also prevent erosion control, which is an ongoing problem here in the fearsome 50s in the Falklands. The winds are very persistent, and the coastlines are threatened by these high winds. And another threat to tussock grasses are herbivores. So there are no native herbivores to this landscape, yet over 140 years of grazing by cattle and sheep have really decimated these tussock grass populations down to 20% of what they once were 140 years ago. Ongoing oil exploration and production in the seas around the Falkland Islands are ongoing and projected to increase in the future, which is a threat to the marine biodiversity as well as the coastlines. And the increasing frequency and intensity of storms along this temperature gradient in this part of the world is projected to also pose a threat to the coastlines. So the Falklands are here in what's known as the southwesterly wind belt. And the southwesterly wind belt is a really important component of global circulation. It's a place where the winds are very persistent because there are so few land masses here to create friction to slow down the wind. And the wind belt it fluctuates seasonally, and it fluctuates in its intensity as well as its position latitudinally. So it moves equatorward and poleward. The proxies that are coming out of this region, well, so there aren't that many land masses, and so we don't have that many locations to take or collect proxies from to establish what the past climate history was doing. And but the proxies that we do have show some contrasting evidence at different points in time. We have about what the southwesterly wind belt was doing. And we have records from foraminifera, from ocean cores, we have ice core records, pollen from plants, as well as cellulose from tree rings from southern Patagonia, as well as Australia and New Zealand. So unfortunately in the Falkland Islands, there aren't trees, but I'm proposing to use cellulose from the tussock grasses in a similar way that they use cellulose from tree rings. So this is how a tussock grass grows. You have the green leaf material that's green all year long, growing on top of a fibrous pedestal of dead leaves. You can see that here. And this forms tussock peat below. And sometimes this tussock peat can be as deep as 11, 12 meters in some places. And the really interesting thing about this system here is that since it's sitting up on a bog, this whole thing is called a bog, we hypothesize that the water that it's using is coming solely from precipitation. So that becomes really interesting when you're trying to understand how this grass records precipitation and temperature. So we were very fortunate to go down to the Falklands last December. We collected sediment cores from different places, but this place in particular is an eroding peat bank. And today there are no tussock grasses here, but what we did find, and which is really cool, is that throughout the entire column that we excavated, we have preserved like whole leaf pieces. And we really need to use this for something to reconstruct past climate, because this is a really great archive. But the problem is we don't know how tussock grasses record modern precipitation and temperature and relative humidity today. So I'm proposing to use stable isotopes as my tool to look at how tussock grasses record these climatic parameters. And just very simply, we could use oxygen and hydrogen and carbon, which are elements, and these elements have two or more forms. And for example, one can be a heavier form and one is a lighter form. And based on these weights, we get these global patterns in precipitation and as well as in plants. And so looking at delta 018, you can see that the purple here is really depleted, and the high latitude regions show depleted 018, and the lower latitudes show higher or an enriched delta 018. So in a rain cloud, the heavier molecule is going to fall out before the lighter molecule. And hydrogen works in a very similar way. And when we combine stable isotopes of hydrogen and oxygen, we can come up with what's known as a local meteoric waterline that gives us like a fingerprint of where this precipitation or where this sample came from. And you can see this, you get a regional signal as well as a seasonal signal. And in plants, we're going to look at carbon. So plants actually discriminate between the heavier isotope and the lighter isotope. And when the conditions for the plant are not favorable, like when it's water stressed or when the temperature is too high, the plant is going to discriminate against the heavier molecule because it's less efficient to use the heavier one than it is the lighter one. So we see patterns in plants. One thing that I've got to keep in mind, because there hasn't been work done on this before, is that there's a body of literature showing that one leaf blade could show variation. The isotopic composition could be variable within this one leaf blade, because this is the older portion of the leaf and this is the younger portion. And so this is just something that we have to keep in mind as we begin to quantify what modern tussock grasses are doing. So the question that I'm asking is, how do the isotopic compositions of modern tussock grasses reflect modern precipitation, temperature, and humidity? And this is an image of the Falkland Islands. The dark green is the higher rainfall regions, and the purple are lower rainfall regions, ranging from 200 to 1,000 millimeters per year. And I am going to set up sampling stations here in geographically spaced out and within the gradient of precipitation variation here. And so at each of these places, I'm going to set up precipitation samplers to collect monthly composite rainfall and then sample this rainfall for the stable isotopes and nutrients, which is part of the bigger picture. And then doing this over 1 year, I'll be able to construct this local meteoric waterline that will give me an indication of the source of the storms and at the temperature at which they may have precipitated out. The other thing I'm going to do is measure temperature and relative humidity using eye buttons at each of these locations and collect leaves from the tussock grasses at each location to analyze the stable isotopes of carbon, oxygen, and hydrogen. So my expectations are that the modern calibration will allow me to understand how the tussock grasses are recording these climatic parameters in order to use this archive that we found. And then we can compare these isotopic compositions to other paleoclimate records of the region, like tree rings and ice cores. And with that, I would like to thank Dan and Betty Churchill for funding this first expedition down to the Falklands, my advisor, Dr. Jacqueline Gill, and Drs. Majewski and Sneed for helping me with the precipitation samplers, and all of the donors from our crowdfunding experiment. Thank you. A lot of you are out here today. Thank you very much for supporting that. And the South Atlantic Environmental Research Institute are collaborators in the Falkland Islands. And Kit. And I'll take any questions. Yes.
Hey, is it feasible to do like any kind of like microcosm or mesocosm or plot experiments where you like kind of do different treatments of heavy precipitation versus light precipitation?
Oh, like controlled experiments?
Yeah, exactly.
Yeah, definitely. So in situ, or
maybe, yeah,
maybe so. It's definitely something to think about. Looking at how the isotopic composition varies, like in a growth chamber, like how the plant response to relative humidity and the amount of rainfall would be really interesting to do. People have done that with other grasses, but
Yeah.
yeah. So
These look enormous though, so it might be like.
right, yeah, they can be up to 4 meters tall.
Okay, yeah.
Yes.
I think we talked a little bit about this last year, but because of the New Zealand similarity with New Zealand.
Yeah.
Well, have you checked, it's a lot easier to get to the Auckland Islands or Chatham Islands than it is to get to Auckland. Is there an ongoing project there?
In New Zealand with the tussock grasses?
Yeah, particularly right in the southern.
Yeah, I do remember you asking me that. Not that I know that they are working on a rush, which is another type of non-vascular plant, and doing a very similar study to see how rush records temperature and precipitation. This has been done with other non-vascular plants like mosses, which create large peatlands. So it's never been done with tussock grass, but they are doing it with rush right now.
There's a lot of tussock there too.
Yeah. No, it would be really cool to look at a latitudinal gradient after this is established.
All right, next up we have Lynn Kaluzinski, who will be talking about determining surface and basal crevasse extent across the McMurdo shear zone through GPS and GPR surveys.
All right, thank you for that, Nora. My name's Lynn, and I'm a first-year PhD student. And today I want to go over just a brief overview of the project that I'm working on that's within its first year. And then I want to talk about some of the preliminary data that we have from our first field season. All right, so first off, what is a shear zone? All right, if you're not familiar. So a shear zone is a boundary that accommodates a gradient in motion. So you can imagine a great amount of friction happening within that boundary. And because of this, there's localized shearing, which causes deformation. And so when we're thinking about ice shelves and shear zones within ice, we normally associate shear zones with crevasses and fractures. And so for an example, on the right is Berg Glacier. And so shear zones kind of formed along its sides as the faster moving ice flows outward into the Ross ice shelf meets the slower moving ice. So why in particular do we want to study the McMurdo shear zone? Well, so the McMurdo shear zone is on the lateral margin of the Ross ice shelf, the western margin. And so it lies between the South Pole and the McMurdo stations. So you actually have to cross the shear zone to get between the two. And so the South Pole traverse has to go between these two. And it's incredibly important in the transportation of fuel and supplies. All right, so it's really important for us to know how this shear zone is going to act in coming years and whether it's going to be a viable place for our South Pole traverse to cross. And for safety reasons, this is an excavated crevasse in the area. All of the crevasses there are actually closed, but this is what lies beneath, in some cases, really large crevasses. So it's kind of it's a safety hazard in many ways. And, and in particular, in 1991, there was a tragedy of Linda, who fell in a crevasse towing 30,000 pounds of dynamite. All right, Linda is a tractor, and the people inside her were fine. They were really lucky to be alive, but it kind of woke us up to the idea that this area needs to be monitored in order to cross there. But more importantly, why is it? Why do we want to study it from a scientific perspective? Well, as I mentioned, it's the lateral margin of the Ross ice shelf. All right, so it is incredibly important to study the stability of this area. Many people believe that Mina Bluff, which is right at the southern tip of it, is actually the pending point of the Ross ice shelf. So it's incredibly important for the overall stability of the Ross ice shelf. And so what's causing the shear zone is as ice is flowing from outlet glaciers all the way down, it's getting caught on Mina Bluff and it causes a great amount of rifting. And so the shear zone is caused as the faster moving ice on the Ross ice shelf side comes in contact with the slower moving ice on the McMurdo side. So really important for future predictions of sea level rise is to determine if this area is weakening. All right, so the data sets that we have and what we want to accomplish within our project, we have GPS and GPR surveys, and we hope to accomplish 3 field seasons.
with the overall research objective being to connect GPS-derived strain rates along the surface with what's going on underneath. So the crevasse spacing and orientations to get a full 3D picture of what's going on. So the GPS grid covers a 5 by 5.7 kilometer square. This is not working anymore. Right around here. And so in order to do the GPR, the Dartmouth School of Engineering, they have a lightweight robot seen on the right called Yeti that tows 2 GPR antennas back and forth across the shear zone to get that data. And so the antennas are of 400 megahertz and 200 megahertz. And for the GPS grid, we actually covered 12 by 12 kilometers, so a little bit larger than that GPR grid. And we surveyed 29 different spots. And so from that, I was able to put together a velocity contour map seen on the right. And from our preliminary data, it's giving us kind of an idea of what's going on and what we expected. There's a really strong velocity gradient across, with velocities on the Ross side of around 500 meters per year and 200 meters per year on the Murdo side. And towards the middle, right around here, where you see the tightest grouping of these lines, that's where the greatest velocity gradient is. And so that's where we would expect to see the largest amount of strain. So just to give you a kind of taste of what we're seeing in the GPR data, this is part of our 400 megahertz data. It's part of a transect, so it's 2 kilometers across and 20 meters down. So it's giving us an idea of what's happening in that fern layer. And it is kind of hard to see, but you do see some stratigraphy across and some folding and faulting. But in particular, all of these really nasty dark blotches, these voids, these are crevasses. All right, that's what we're seeing. And some, it's hard to see even, now it's working, comes all the way up to within a meter of the surface. So a very scary picture of what we're seeing in our data. And so for a sense of scale, the largest one that we found is 16 meters wide. That's pretty incredible. That's comparable to this really monster crevasse that they excavated when they were looking into the road. The figure on the right is 2 meters tall. So this is 16 meters deep. So and that's how wide this crevasse is. So huge. And we also found something really interesting for our 200 megahertz data as well. We were able to see about 180 meters down, and we picked up on something around 150 meters, or right around here. So we found a really sharp interface that we believe to be an interface between inglacial ice and basal marine ice. So basal marine ice is this ice that freezes on underneath the ice shelf, and we believe that we're picking up a really strong signal right here because it's a difference in density. What's particularly interesting is it wasn't just straight across. There were many gaps in our data, and those cuts we believe are fracturing and basal crevassing within that layer of ice. So this is really interesting, and we get a full picture of it. So this is a transect of the entire 5.7 kilometers across and 180 meters down, all stacked together so we can kind of see a full spatial range. But we found a really strong visual correlation between the surface crevassing and basal crevassing. So you can kind of see all these lines are indicating those crevasses. So really interesting, particularly because basal crevasses, there's not a lot of literature on them. They're very hard to study. So it's particularly interesting because we want to know how they're formed. So there are 2 hypotheses that we've kind of come up with. The first is what we found from a little literature that is out there, that in fact they might be formed at the grounding line. All right, so the grounding line's way up glacier, and so it's believed that as the ice shelf becomes afloat, that flexure of the ice shelf causes opening of crevasses right at the grounding line. And so if that's the case, then the correlation that we see between those crevasses in our data might just be coincidence. And in fact, those crevasses are inherited from up glacier. But just by looking at that data, we've come up with an alternative hypothesis to say, well, maybe the fact that we see a correlation is because there is one. Perhaps they are formed from the same processes that's happening on the surface as on the base, that shearing is causing those crevasses to open. And so why would we pick up on that all of a sudden at this interface? Well, it may be that this new ice, this freeze-on underneath the ice shelf, is weaker because of salt inclusion or because of impurities. And that's why it's all of a sudden starting to open up. So in conclusion, to my future work, I really want to just try to figure out what is going on and determine which one of these hypotheses are correct. Maybe they're both happening. So that's important to look into. And so how will I do this? Well, I really want to connect the basal crevasses that I see in my GPR data, how they're oriented, how they're moving through time, and connect that with the strain rates that I can derive from my GPS data along the surface. And we really have hopes for next season to get lower frequency from penetrating radar to see all the way to the bottom of the ice shelf. We think there's another maybe 50 to 80 meters that we're not seeing to get a full picture and also see more better into the glacial ice as well. So with that, I'd like to acknowledge the massive amount of help, especially my advisors, Gordon Hamilton and Peter Fritz. And with that, if there are any questions, thank you.
Lynn, would the orientation of the basal crevasses tell you anything about the origin?
I believe so. I think in particular, if they're caused by shearing, I would expect that they would be 45 degrees around from the way that from a cross flow. So I think that'll really help, and we can kind of tease that out from our data, hopefully. But as far as, I'm not sure if the orientation would tell us too much from if they're inherited from the grounding line.
Well, if they were formed at the grounding line and they were being carried by the shear, they would have been rotated.
Yes, that is true. There's just, they would have been inherited a long way up, and I think it'd be kind of tough to see how far they turned, but it would give me something.
You're showing an awful lot of hyperbolic reflectors in that basal ice, and they could be crevasses, but they could also be something frozen into the ice, something frozen on from the bed. Do you have any relative feeling?
I think the smaller hyperbolic diffractions, I think I have an extra slide. This is kind of hard to see. The really strong ones that are really wide, those tend to be more crevasses, where in my 200 megahertz data, you might have seen those smaller ones, those might have been more fractures. But as far as teasing out if there's some, are you saying impurities, for example?
Boulders frozen on at the base.
Oh, I hadn't thought of that. That would be very interesting. If so, and I think we'll be able to get a better picture from lower frequency data this next season as well.
Okay, moving along. Next up, we have Dr. Gregory Zaro, and he'll be talking about urban transformation and landscape change at the Naden Archaeological Site in Croatia.
I'm going to go without the mic. I teach to 300 students in the fall and never use the mic, so. Well, thank you all for being here. I have no conclusions yet, no data. This is a start in a new direction, this project. This is the first chance I've had to really share with people here. It started in 2013. I went on a Fulbright to Croatia with just the idea of exploring some of the themes that I've been working on in Latin America of agricultural landscape change, urban change, and combining those efforts into a single research design that really looks at landscape change through time, the role that humans play in that change, and how they affect landscape change and even respond to climate and environment outside of those social and political systems. So I came to Zadar and had a little office in the university here. It's a ridiculously fortunate location for university. And I explored a lot of literature. I engaged with a lot of faculty at the university. The idea was to really explore if this is a possibility, if there's interest in engaging in these different disciplines and bringing them together for a problem-focused research. And I came away really excited about it, went back in 2014 for another sort of planning visit, and now we have money from National Geographic to start up this summer for excavations, and hoping of still building this long-term foundation for understanding landscape change through time and how it articulates with climate in human societies. So this is Zadar, and it is a 3,000 to 4,000 year old city, and we'll hear a little bit more about this and why Nadine as an archaeological site is the appropriate one to pursue here. So for those of you not familiar, Zadar is on the Adriatic coast in coastal Croatia. It's a very beautiful setting. The site of Nadine that we'll be spending our time at this summer is just outside, and this area is called the Ravni Kotare. It's been historically very important agriculturally. It's been characterized as one of the most urbanized landscapes in antiquity along this stretch of coast, and it's one of the few low-lying zones. Coastal Croatia is quite mountainous through most of its expanse, with the Dinaric Alps just behind this Ravni Kotare region. So it seems like a good location to explore these ideas of the evolution of human society and landscape through time. A couple of things. As an archaeologist, I like to think we're the most important one in the room. We are the hub of the wheel that draws in all these other disciplines. We're necessarily interdisciplinary because people are complex, they're biological, they're involved in a whole suite of environments around the world. We're very complicated socially, but we come up with good questions, but we can't answer them on our own is the problem. So when we look at problem-focused research as archaeologists, I look in the 21st century. What are the issues going on today? Surrounding Zadar, it's rapid urban growth and expansion, a lot of rural to urban migration. People are abandoning landscapes that are characterized as more traditional in a Mediterranean environment. Sustainable development, resource conservation, policy, these are all major concerns confronting a rapidly growing cityscape, particularly since the breakup of Yugoslavia and solidifying Croatia as a nation state, now a member of the EU. It's really exploding in growth, and tourism is playing a major role of this, particularly in the summer months. There's a nice big cruise ship here in port. This is a major aspect that's drawing people from their fields, from these traditional landscapes, and investing in a few months of really intensive tourist activity through apartment rentals and leasings. That supports them for the entire year, but it leaves these landscapes sort of void of people, and people are actually stabilizers in many contexts. Interestingly enough, they tout in the Croatia's tourist board the Mediterranean as it once was, and it completely ignores the fact that these are human-dominated landscapes for thousands of years, arguably going back at least 8,000 years ago with the introduction of farming and domesticated animals. These are wholly anthropogenic landscapes, and so deciding what is Mediterranean has evolved for 8,000 years. Deciding what goes forward in terms of conservation practices is a daunting task at this point, because there isn't this simple natural baseline. As everyone in this room knows, there isn't one in the natural world either, independent of what we might call a human ecosystem. But these fishing, farming, urban centers, this goes back multiple thousands of years in this part of the world. Compounding this problem, the latest IPCC reports, which echo the earlier report, is that in this part of the world, it's kind of hard to see, but here's the Adriatic. Summer months temperature is projected to be higher. In summer months, precipitation is projected to be much lower. And this sort of is the confluence of influx of a non-resident population for the tourist season, where water is going to be a big stress factor going forward for Croatia. So, as an archaeologist, Zadar is a beautiful city. It's a 3,000 to 4,000 year old city, but I have a problem excavating in a city that's still being lived in, right? So we think about, as an archaeologist, the problems of urbanization, or how we might characterize urbanization over the long term, over a 3,000 to 5,000 year period. This is what we see archaeologically. Generally, higher populations, greater nucleation, cycles of growth and decline, sometimes collapse or abandonment, greater impact on landscapes that create wholly new urban ecosystems, settlement expansion, agricultural intensification, increased need for building materials, a greater ecological footprint in the local and regional space that it occupies. We can't do anything like that here other than a historical assessment. And going back in time, Zadar is this interesting palimpsest of architectural imprints from previous years. So you have fortification walls that were Roman-induced as a Roman colony, late antiquity, a few centuries later, medieval fortification wall segments are still standing. The Venetian wall here, which is still around the harbor side of the city, they removed it along the seaward side. This city itself has been a vibrant place for 3,000 to 4,000 years. The great thing is that we can look at its hinterland because cities are not bounded entities. They are supported by their hinterland. So as an archaeologist, we can move outside of these intensively occupied areas. Where it's an area of intensive food production, Uglian Island is still transected with field walls, olive groves, terraces, vineyards, along with Roman mills on this island, suggesting that people have intensively managed this for at least 2,000 years. Notting itself, the great thing about this archaeological site is that preliminary work back in the 80s at least suggests it goes back probably 2,500 years or so. We don't know the chronology very well, and that's a big part of what we're going to do this summer, is sort out the chronology. It's in Zadar's sort of urban catchment area. There's presumably an Iron Age component at its founding. The Romans transformed it into a municipium, a formal municipium called Medinum. There's a late medieval component. There's even a 16th century Turkish fort with a nice drawing of this from the 1700s, I believe. Some of the walls presumably still standing from this Turkish fort here. But this is what we see today at Nadin. It's fully an archaeological site. The modern village is at the margins of it. But it exhibits, if we count the modern village as part of this settlement system, it's been occupied probably intermittently for the last 2,500 years to 3,000 years. This serves as a long-term gauge, treating Nadin as a catchment basin to see how the landscape has changed through time. Right? So humans are like little pack rats in a sense, bringing things back to town centers, and we can look at how that environment that they've interacted with has changed through time. It's quite complex. If we look at the map produced in the 80s, here's the megalithic wall that is either Roman or pre-Roman, and that's this dark line here. Not much has been done within that megalithic wall. A little bit of test units outside, but we don't see much of this today because it is so overgrown. Satellite imagery, again, it's mostly scrub forest. This is the fortification wall. If you overlay the map, it fits pretty well. And you can kind of see the modern extent of the site into where the village is today of Nadin that stretches off the satellite photo here. But what we're projecting to do is to scatter plot excavation units, 5 by 5 meter units. These are big. We have an army of students from UMaine and from the University of Zadar that will be working with us. And we're going to scatter plot them around initially and then build off of those to really try to identify depth of deposits, the depositional sequence. We're going to radiocarbon date a number of these units to really get a good sequence out of this and see how far back we can stretch. And if we can identify particularly cultural changes in the context of broader environmental changes that are noted, like the Roman optimum, medieval climate anomaly, a little ice age. Some of this work up here is very interesting. Paul's been part of this, of looking at the intersection of science and history and identifying long-term climate changes. And the Croatian Geological Survey is doing a really strong environmental reconstruction project, the lost lake landscapes of karstic Croatia, and they're going to be instrumental going forward as well in helping us to articulate and ground our data in what the broader environmental signals are looking like over the late Holocene. So we're excited about this. We hope this will be a project that is long-term, and we expect there to be fully a public outreach and education component within Croatia and even back here as well, of how we might apply these to the broader interest of landscape change, urbanization, in a globally comparative sense. So next year, we will hopefully report on the results of this field season. So thank you. Yes.
Greg, one of the landscape components that you did mention has to do with tectonics and seismicity. Of course, this area is pretty bad.
Right.
Can you see any of that directly?
I don't know yet in terms of what we might see in that sense, but I do know that the precipitation and the water, groundwater, and all of this is going to be a major factor in looking at the sustainability of people on this landscape through time, and tectonics is going to affect those aquifers a lot. So that's something that we're going to work with the Croatian Geologic Institute on how that might play a role.
Great.
Thank you.
All right. Next up, we have Dr. Gordon Hamilton, and he'll be talking about recent changes in the northeastern sector of the Greenland ice sheet.
Okay, this is just a 2-minute talk. So many of you know that I've been working a lot in southeast Greenland on rapid changes in glaciers there. Glaciers down here exceed Annie's criterion for getting really excited about them. They move at 25 meters per day or sometimes 50 meters per day. They've responded largely because of climate forcing. But now we're interested in looking at other parts of Greenland, see where else we might see one of these ice sheet responses to forcing from either the atmosphere or the ocean. And northeast Greenland is kind of attracted our attention for the last few years. It's special in Greenland in that many of the glaciers end in floating ice tongues or ice shelves. In fact, it's the only place in the northern hemisphere where ice shelves still exist. Ice shelves that you heard about in Lynn's talk in Antarctica. And although many people think that this part of Greenland is relatively stable, I'll show you that actually it's starting to change in quite important ways. And here is just 2 satellite images of one particular outlet glacier ice shelf system, Zachariah Istrom, 1990 and 2014. Previously an ice shelf. Now the terminus is terminating in open ocean water. Just a zoom up of that. This loss of this ice shelf here amounts to about 200 square kilometers of floating shelf that is rapidly collapsed. As the ice shelf has collapsed, the terminus, as I've said, is terminating in open water, and you can see that the speeds at the terminus have increased. It's like taking the cork out the bottom. You take away the ice shelf, it's providing some back stress on the terminus, and the inland ice starts to flow to the ocean much faster. And it's increased from about 500 meters per year back at the start of the century up to about 1,500 meters a year this last summer. So it's not quite an Annie's criterion for getting excited about it. It's merely moving at 3 meters per day. But still, it's quite an important change. And the reason it's interesting is because the next glacier to the north, Nyakavfjordfjorden Glacier, 79 north degrees glacier, is a similar kind of ice shelf. It's pockmarked with these melt ponds. It buttresses this northeast Greenland ice stream, which extends all the way to the interior of the ice sheet, and trough is below sea level, meaning that once that grounding line is exposed to open water, it can retreat hundreds of kilometers inland and deglaciate this large sector of northeast Greenland. Reason we think this has happened, this is work that Bill Sneed did for his PhD thesis last year, just plotting the positive degree days for a number of weather stations in this part of northeast Greenland. And there's a weak warming trend, but the thing that really grabs our attention is these anomalously warm summers at 2002, 2003. And if we go back to here, I think what happens is that you get this kind of runaway reaction of these melt ponds that are always present on the surface, but they sort of, on a very warm summer, they grow really fast and they're able to hydrofracture the entire ice shelf. And once the ice shelf fractures apart, the blocks are advected away by ocean currents until the terminus is terminating in open ocean water. And so we expect that this, as these warming trends move north, that the next glacier to the north, 79 degrees north glacier, will undergo the same changes. And if that happens, then we're looking at 1.5 to 2 meters of sea level rise happening very quickly.
Okay. Next we have Dr. Ivan Fernandez, who will be talking about a vernal transition on the move in terrestrial ecosystems in Maine.
We're done.
There we go. Okay. So this is another 2-minute update. Has to do with the vernal transition, which has become a sexy term in ecology, having to do with what we're still waiting for to happen here in Maine in 2015. To give you the sort of framing of the issue, as we all know, the frost-free season, growing seasons, et cetera, increased by or the frost-free season, yeah, is increased by about 2 weeks over the last century, with more in store. A lot of what we've seen, and a lot of the biological experts in the Institute talk about phenology, the way organisms respond to the changing seasons, and now that the seasons are on the move, how they're responding to the change in the changing seasons, and particularly the asynchrony in those processes, which we poorly understand. We've sort of expanded that. I'd like to talk about ecosystem phenology, so the intersection between the biogeochemistry, the physical environment, temperature, hydrology, as well as the biological response to these changes. And in particular, this vernal transition anchors in northern latitudes around snowmelt, and again, that miraculous point that we're still waiting for in 2015. And in the middle of the figure there shows some data from our continuous monitoring at our Bear Brook watershed from last year by Kaizad Patel in my program. The gray area is the snowpack. The upper panel is air temperature. The lower panel is our calibrated stream. And so what you see is the day the snow leaves, which is hopefully soon. And actually, of course, this is happening all around us right now. We see a really immediate and rapid increase in soil temperature. And being a soil guy, I like anything about soils, but that begins a cascade of events that are physical, chemical, and biological, and that we really poorly understand, and that has a lot of impact on everything that follows going into the growing season. So that's led to sort of a family of activity going on, focusing on winter. The vernal transition, we're looking at in a number of places, particularly the point of transition and then subsequent biogeochemical, microbial, and then sort of the standard phenological processes. This year, 2 grad students, Corian Tararu and Kaizad, did a snow removal experiment, and that's over here in University Forest. They spent their entire winter shoveling to keep the snow-free plots free. There's dramatic, we have eye buttons buried in all of the plots, and there's dramatic differences in the temperatures. And so we really should see quite a contrast in the dynamics of what happens during this vernal transition. That's also led to K-12 programs. We've had several that we've done, particularly Sarah Nelson is a lead in collaboration with the Skudik Institute. And one right now, Jasmine Saros is part of this one as well. We have 14 schools, 16 teachers, and about 600 students in the 3 climate zones in Maine, all winter long out measuring measuring snow, characteristics of snow, and of course, they're all very excited about now measuring aspects of the vernal transition. And as a result of those activities, there's a winter ecology interest group that has sort of emerged in the past few months this winter that will continue to look at collaborative projects, perhaps a seminar series next year, and anyone who's interested, let us know. That's it.
Next, we have Dr. Ellen Enderlin, who will be talking about iceberg melting into Greenland glacial fjords.
So this is a project that I started working on as a postdoc with Gordon. Now I'm sort of continuing on, and I'll be talking really quickly, since this is a 2-minute talk, about results for 2 fjords in Greenland. I'm looking at Jakobshavn Isbrae, or Lillesab Fjord is right here, and then Helheim Glacier and Sørmelek Fjord are over on the east coast. And I'm working on expanding this analysis to about 12 glaciers and their connecting fjords. And as a glaciologist, I'm looking at iceberg melting because I'm trying to see if spatial and temporal variations in iceberg melting can be related to spatial and temporal variations in glacier melting. So at these glacier termini, Gordon talked about a second ago that one of the ways you can cause these glaciers to accelerate is by sort of breaking up the ice at the terminus and letting the cork out of the bottle. Another thing you can do is you can increase melting below the water line. And that's what I really want to look at. And obviously that's hard to go out into these fjords and collect observations and sort of back calculate melting of these glaciers. So I'm looking at icebergs. And I'm looking at their melting, and the way I'm doing that is I construct really high resolution digital elevation models. The satellites or the worldview satellites, they have a 0.5 meter pixel resolution. So if you laid down on the ground, the satellites could see you laying on the ground, which is pretty fantastic. And I use those to make DEMs, and then I difference the iceberg surface elevations in time to calculate the volume of water being lost by melting of these icebergs. And these two images here just show you footprints for these DEMs for the 2 glaciers that I've been looking at. And I've manually sort of picked out these icebergs at different time periods and been able to calculate their freshwater flux, which is on the y-axis, and estimate the submerged area, which is on the x-axis of these 2 plots. And when you look at these, each different time period is color-coded, and then I fit a best fit linear trend line. And when you look at them, you see that the slopes of these trend lines differ quite a bit for the different observation periods. But in general, for each time period, you can see that the freshwater fluxes vary with the submerged area. I think this is really cool because this means that if you take a glacier and you discharge more icebergs into the fjord, there'll be more fresh water that's discharged into this fjord because of the iceberg melting. But also you could just take your icebergs and break them up into little pieces. So if suddenly you don't put more ice in, but you just cause the calving style to change so the icebergs are each smaller, that will cause the freshwater flux to increase. And if you think of it, if you have an iceberg or an ice cube and you put it in your drink, and it won't melt it will melt very slowly if it's a big ice cube because it has a very small surface area relative to the volume. But if you take it out, you break it up into a bunch of little pieces and you put it back in, you're going to dilute your drink very quickly because it'll now melt very quickly. It's the same thing going on here. And the slopes are also approximately equivalent to the melt rates for these icebergs. So you can see that there's some variation about these best fit trend lines showing you there's some variation in the melt rates. But overall, they're pretty comparable to glacier melt rate estimates. And so I hope that by expanding this analysis more to about 10 other glaciers, that I'll be able to say something about how glacier melt rates are changing spatially and temporally. Right, and I'll be done with that.
All right, next we have Dr. Carl Kreutz, and they'll be talking about using geophysical reconnaissance to expand ice core hydroclimate reconstructions in the Northeast Pacific.
Thanks, Dora. Okay, I'm standing between all of us at lunch, so I will make this quick. Luckily, much of what I'm talking about here has already been touched on in other talks today. First of all, Andy pointed out to us very nicely that it snows and rains a lot in the Northeast Pacific, and that is absolutely true, particularly in the coastal regions. But not only does it snow and rain a lot there, if you look at the precipitation anomalies, and by that I mean if you take years in the Pacific where there's La Nina-like conditions in the tropical Pacific and subtract from that years where there's El Nino conditions in the tropical Pacific, you end up with a precipitation anomaly pattern in the Northeast Pacific that looks like this. And so there's anomalously high precipitation during La Nina years along the coast, but a lower precipitation anomaly inland in Alaska and also down here in the more southerly part of the coastal ranges. So we, over the past 10 or so years, have collected a lot of different ice cores from that area with the goal of trying to use that anomaly pattern to reconstruct past climate change. Because if we can tell something about that anomaly pattern in the past, we can look at interannual scale teleconnection patterns. So from those ice cores, we have a lot of really good detailed accumulation rate records, which is what we want to use to reconstruct precipitation. This one happens to come from the Eclipse ice field in the St. Elias Mountains. It goes back about 450 years. It has a really good chronology. It's annually dated. The problem is that the ice is flowing and compressing as you go deeper. And so you have to correct for that to back out the actual accumulation rate record. If the ice is flowing in a vertical sense, that's a pretty easy problem. But if there's any three-dimensional aspects to the flow, it becomes a lot more complicated. And particularly down here in the deeper part of the record, that's probably absolutely the case. So what we're going to do, and when I say we, this is Seth Campbell and Don Winsky and a bunch of other folks who've been working on this. We're going to go back to many of these ice core sites that we already have the cores from and really put together a detailed geophysical framework, looking at surface topography of the ice, all the internal layering from GPR transects, and also bedrock topography, and then use that to sort of refine this three-dimensional model that Seth has already built and published a couple of years ago, and use that model to really correct these accumulation rate records from each of the ice core sites, so we can then put it all together in that spatial array of ice cores and reconstruct these spatial precipitation patterns. So that's 2 minutes. That's going to be a lot of work, but anyway, that's what keeps us going. All right, so it's lunchtime. Becky, however, is guarding the food out there, and she tells me she's not going to let anybody have anything until we all gather at the front of the room for a group picture, which Nora has graciously agreed to take. Yeah.